really efficient in terms of packet processing. And really, updating the packet header, the things that we restrict ourselves to, it's pretty easy in hardware. But the LPM lookup, the real forwarding of packets according to those routes that were installed, those IP routes that were installed, that's the more difficult bit. And that's where we kind of talk through the LPM process, the longest prefix match process. So, unexpectedly, we did not use the whole time. So, questions? Hey. Yes, usually. So how this kind of actually ends up tending to work is that you have the fairly fast first processing, the breaking down of the packet, get into the chip and the forwarding chip. And in this case, we just needed to do an LPM lookup. We just need to do one lookup. But sometimes we have to do multiple lookups in different databases to be able to figure things out. So that's really where the core of the cycles end up being spent. The fabric part is also quick. So the real constraint when we're looking at these routers is usually about, well, how fast can that chip go and do the functionality that it needs per packet? And we look at that and we think about, well, how many packets are going to arrive? And why we talk about things like the size of the packet is because a 400 gigabit link that's got 1,500 byte packets is many fewer packets than if they're 64 byte packets. So what we do is we spend essentially a fixed amount of time per header of a packet, not the size of the packet. So we really care about when we're talking and doing some of these design analyses on these forwarding chips, we're saying, well, at 200 byte average packet size, we can achieve this rate. And so that's where sometimes the number we talked about, the capacity, the R number of speed per link, might not actually be the number that you saw on the line rate. It might be lower than that. It's like the little Linksys router I put up. There's no way that thing can forward at 1.4 gigabits per second because it's doing a lot of things in software. So even though you could give it 1.4 gigabits per second of traffic, it's just not doing it because it's spending a lot more time in the lookup phase and in the lookup phase and in the forwarding than it would need to do to sustain that line rate. Sure, on the right-hand side. So historically, how that works is, so this is an internet interconnection. It's called peering. It's when two networks connect to each other. And there's a few different ways that they work. One is that you buy from somebody else. So I go to a provider and I say, hey, level 3, I want to buy access to the internet. And they sell me access to all of the internet. And they charge me for that link. But then there's also connections where I say to, maybe I say to Verizon or I say to Sonic or some ISP here, and I say, hey, I'm Google, I'd like to send you traffic for YouTube, and I'd like it not to pay for it, thank you. And you'd like not to pay for it. So we have a bit of negotiation, and we say, okay, yeah, great, we'll interconnect with each other privately. And how that tends to work is that then we agree where it's going to be. Maybe we'll do it in multiple places across the country, and we'll go and then, somebody goes and physically plugs in a cable. One of the things we've done at Google and why we've spent so much time in the management place, we have a lot of links like that. Thousands of links like that. And they all need capacity upgrading things. So we've actually worked on a way that that's software automated. So a lot of the time when somebody comes and asks us for a link, the first time it really reaches a human is when the human is plugging something in. And then everything else is machine-driven or robot-driven from there. But there's kind of the commercial negotiations that go into it, and then the practical, technically setting it up. And why the management plane is really important in this space is because someone needs to tell it, we've got this link is going to go between, Sonic and Google or AT&T and Google. We're going to run BGP on it. So we have to tell the router what to be doing in terms of control plane protocols on those links too. Sure. Yeah, so that's why we're kind of picking the simplest possible model. There's a lot of sort of ways that we think about how to manage that buffer occupancy. So you might take that into account. Even if there was just a single class, you might say, well, I don't want to be full. And some things like TCP, well, it's better if I drop some packets and they back off and they don't keep sending me. So you might do randomly dropping packets before the buffer was completely full. But then if you've got different classifications, you might say, well, why would I want to drop this really important packet before I drop this other one? So you have a weighted random early detect, that's what we call the random dropping, that gives you a way to manage that buffer to say, okay, well, the buffer can be this full of these packets, and if it gets greater than this amount of full, then start dropping those packets, and you end up with these slopes that kind of give you a complex algorithm to say, based on the classification, how should I use the memory that's available to me? No. I think that there are local networks where flooding when you don't know what to do is okay. Like you might learn, there's some learning. But in IP routing, we don't do that learning, right? We don't look and say, well, I saw this packet on this port, so therefore it must live, like that address lives over there. We have the control plane protocols to deal with it. So what would happen if we flood the packet? Well, probably we send out the same port we just got it in. And the guy on the other side, or the router on the other side would say, well, yeah, you should be forwarding that. And so then we end up with routing loops. So like where we just have routers or different parts of networks that are just passing the same packet backwards and forwards until the TTL expires. Why the TTL is really important, right? We don't want that infinitely going around. But no, in general, we want to drop the packet. It's usually a good signal. And if you don't want to drop the packet, that's why you have the default route. That's so when your laptop is connected to a network, well, it doesn't need to know about the whole internet, right? And if we think about it, it just needs to know, well, it's over, like the internet is via that router over there. So the next hop for everything is set to the default route. And so if you don't want to drop a packet and you want to have somebody else handle it for you, then the default route gives you that, rather than flooding. That depends on the hardware. So and this is somewhere else where we make hardware trade-offs. So if we're thinking about the kind of chips that we might be building and talking about doing 400 gigabits per second on 36 ports, or maybe there's 2 chips per line card, so 18 ports, then 8 buckets per port is probably normal. But if we think about something that takes in some device that connects a lot of broadband subscribers, a lot of homes to it, then in that case we've got lots of individual subscribers, lots of individuals that are all connected to the same thing, and we might want to classify between them. So at that point we can get up to 256,000 classifications per port. And what does that come with? Well, it comes with a bunch more memory, it comes with a bunch more complexity for managing them, and so that then means that the complexity of the line card goes up. Usually what that means is then the throughput goes down, because we've got much more to do per packet. But also we just used a bunch of we've essentially got something that's probably 60 centimeters by 40 centimeters, 2 feet by 1.5 foot-ish. That's the whole amount of PCB that we could deal with. So the more things that we put on it that are doing not forwarding, the less forwarding we do. And so the density, the kind of capacity of those routers tends to be lower. But in those cases, we can end up with extremely complex scenarios, and they're usually in this kind of subscriber management where we're dealing with individuals rather than ports. Now, if you're internet network, you're really only dealing with ports, and you're probably dealing with one class per port, so you maybe don't even use those. Internally to a network like Google's, though, we have different things that are on the network. We have traffic that's to do with copying between machines. Well, maybe they can just come back when the network's less busy. But then we have traffic that's, you did a search on google.com, and you get really annoyed if we don't deliver that. So we want that to be more important than others. So that's where we have some level of classification, even though we're carrying just internet traffic. In that case, it's our business objective.
You mentioned that number of processing one item in requirement second and kind of trying to increase rate. And with the line rate, even if this number is going to get lower, which is pretty impressive, unbelievable. But in a way, processing the packet headers is easy spotting all of this, right? If you take in packets of this rate, you should also be able to do something in the body. Is there anything you can do with the body of this rate, or do you just parallelize? How do you?
I make the joke that I don't know what's past the headers of the packet. For routing, we don't care. so for sticking for these like IP routers where we're doing layer 3 forwarding only, we just look at the headers. Anything else there, actually it's great if it's bigger, right? Because that means that we get some more, we get fewer of the packets per time. But these systems really, they might be able to do some looking into the packet, but we really don't want to get involved in that because we really want IP to be transparent to what people do on top of it. So what we do tend to look at sometimes is we look at, we say, oh, this is IP, but actually inside it's got TCP. And we want to look at things like the source and destination port, but we usually use that for entropy when we're trying to you can imagine that, we didn't really mention it here, but you can have a route that goes via 2 different ports, and we want to figure out how to share, load balance traffic across the 2 different ports. So we might look a little bit into the header. We generally try not to. So, and then if you're trying to do things at line rate, at 400 gigabit line rate, extremely unlikely that you can do anything with the header. So when you see things that do firewalls, which might need to look further, the more complex they get, the less capacity they end up being. And we might be able to do some things here, we might be able to do what we call access control lists. So that's where we don't allow any packet that has TCP port 147. I don't know what TCP 147 is, but apparently we're going to drop it. So in that scenario, we would say, okay, there's this offset into the packet. If you match that this is a TCP protocol in the IP header, then look at this offset in the packet, which is the port number, and drop it. So we can do those kind of simple kind of equality checks. But it's another thing that comes at some cost. Actually, what we end up doing is having more hardware and a lookup table to be able to do those kind of exact match lookup tables earlier in the process. And so it's another place where the more complex you want those inspection of the packet to be, either the more complex you make the router, which probably comes at the cost of capacity, or you just say, well, I don't do them, and I hand it to something else that goes slower to be able to do that more complex functionality. But yeah, we don't really look at the packet header at all, past the packet headers at all. Sure.
How common is it that a buffer will completely fill up and you actually need to drop packet? Is it a common occurrence, or?
Good question. It depends on your capacity planning approach. So when we look at the network, what are we really doing? Well, we're building a graph. It's got a bunch of nodes, it's got a bunch of edges, and then we've got some demands on the graph. So the demands are where the traffic's coming from and where it's going to. And so what we'll do is we say, well, we think that there's going to be this much traffic coming in New York, and we think it's going to be served out of this data center in Tulsa, Oklahoma. And so we then build enough capacity. And so if we built enough capacity, well, it shouldn't get full. But if we haven't, then it does. And then you can then say, well, do I build all the capacity that I have to? So I could go and build, every time I could think about, those guys in search over there, they really want to copy these big amounts of data apart, across the network. So I should always have the capacity available to do them. Equally, it can be a bit smarter and say, well, rather than giving them completely all the capacity that they want, because TCP will ramp up and try and use as much as it can, I can say, well, I'm only going to give it this much. I'm just going to capacity plan that they can do 200 gigabits a second of copy traffic from Tulsa, Oklahoma to Council Bluffs, Iowa. These are the kind of places that Google has data centers that I, as a Brit, was not aware of beforehand. Have been to Council Bluffs, Iowa multiple times, which is not a sentence I ever thought I would say. Nothing against it, I just hadn't heard of it. So in this scenario, we've got we didn't necessarily build all the capacity for them to do that kind of copying of traffic. So in that case, we do have pretty full buffers because someone's trying to use all the capacity possible. And one of the metrics that we look at in the networks that we build is, because we're trying to build these scales that are really, really challenging. We're looking at 400 gigabit ports. We've already got them. We're looking at 800 gigabit ports. They're not being produced yet, but we're already planning on them being there. So we're always at the edge of trying to get the maximum capacity that we can. And so we want to use that asset as well as we can. So we're really trying to say, if the network's 100% full, that's awesome. Because then we're really using that infrastructure that we built as efficiently as possible. So for us, they're pretty full. But in other networks that I've worked in, we had lots of business customers. They're paying a bunch, and they pay us for 10 gigabits of capacity, but they just never use it. But they want it there just in case. And so in that case, those networks had extremely low utilization. And so it really depends on what the network looks like and how much of it you build if you can scale above something, and then how you want to manage traffic on it. So it's kind of an overall view of both the service you're trying to provide. Like your broadband network provider probably says, well, on average, a user uses about this much traffic, so I'll build the network according to this with some error margin.